and say, hello everyone, welcome to this new departure for the Maths Hub, doing follow-up webinars after our in-house meetings. I'm Nick McIver. It looks like I'll be doing all the talking in this session because as far as I can see, none of you have microphones, although you can communicate with me via the chat box on your GoToMeeting window. So do interrupt or ask questions. To get through the content of this, it should take about 30 minutes. So, this is what we discussed at Marylebone a week ago. Here was our agenda. We looked at teaching confidence intervals. We looked at virtual lessons on video and how we could develop those in the future. More details in a moment. Support available from the Institute of Education, and yet another textbook that's coming out, this time a short revision guide. Like all the other textbooks, it is targeted at the AQA course. Sorry, Vivian, the only stuff in print at the moment for your course is the one that you have from Edexcel. So we're going to start by looking at confidence intervals. Oh, first an aside about calculators. The one on the left of the screen that you see at the moment is probably the most widely used one in schools at the moment. That's the one we use. It is perfectly adequate for everything that you need to do at A level and for core maths. However, when the new Spec A level goes online, students will not be expected to use tables. And the one on the left doesn't do the normal distribution. It doesn't have a virtual normal distribution table in it. The one on the right does have a normal distribution function, and I'll show you how that works. The drawback with the one on the right is that it currently retails at about £25. That's the cheapest I can find it online. Marylebone, as a maths hub, was supplied with 20 of them, which they called a class set. Not quite sure how they worked that out. I suppose 2 or 3 for the teacher, 20 is a reasonable A-level set. It's a pretty good machine. Here is the great advantage that this particular calculator has for things such as the normal distribution and confidence intervals. When you switch on the new Casio FX991EX, it's called the Class Whiz, you get this screen. Now, the one on the top left, that icon on the top left, which you move around it using those little aluminium buttons, which are very nice. It's very nicely made. The one on the top left just has it in normal calculator mode. That one there works with complex numbers. This one here is for working with ratios. It works with matrices, various data handling functions. It's a full graphing calculator, but this one here, function 7, essentially does everything a normal distribution table will do for you, but much, much more easily. The way the calculator works, and you'll see the attraction of this for students, is when you choose the normal distribution function, and you'll see it says normal CD, that's cumulative distribution function, rather than messing around with Z values, you simply type in the mu value, i.e. the mean of your distribution, the sigma value, the standard deviation, and you type in the upper and lower boundaries of the interval that you want to investigate. So one drawback with this screen is you'll see it says normal cumulative distribution. It's only giving you the upper boundary. I think for a mean of 178.47, this was looking at something like the interval from 175 to 186. Hi, Colleen. Nice to see you. We're just looking at the using this particular new type of Casio calculator for teaching the normal distribution. So here we are. You input the parameters for the standard deviation and the mean, and you also input the actual raw data points for what's the probability of an outcome between this lower limit and this upper limit. And the calculator will simply tell you the area under the normal distribution curve between those values. You don't need to do any messing around with Z values or anything. In a moment, I'll show you what it effectively does. But it is much, much easier to use than tables. From A-level next year, students will have to use something like this. It remains to be seen what else comes onto the market. This is the Casio 991EX. There's already one around called the ES that does some of this stuff, but the graphics are a lot lower powered, and it's about £15. So that's just an aside. This is the calculator or something very like it that you're probably going to have to be using with your A-level students from next year, because students will not be provided with tables in the exams. Except Edexcel. I think Edexcel A-level have said they will continue to provide tables. Everybody else, you need a calculator. You can use the other functions in various ways, and one of the nice things about the statistical function for A-level is that you can go through all the different regression options, one variable, linear regression, quadratic regression. And you can also, when you're doing single variable outputs, get all your outputs on a single screen. This is very handy for S1. I'm not here to sell you Casio calculators. It's just an aside. So, confidence intervals. How do you teach confidence intervals? I was dreading this slightly because I realized that I'd never actually done them as a student, and this stuff wasn't in my A-level. I've since done them as doing master's level stuff in statistics. So how on earth do you teach it to B grade, C grade GCSE students for core maths? Here is the best suggestion that Lee and I have come up with. This is primarily Lee Baxendale's suggestion. He's the career statistician in our maths department. And the key idea here is the idea of a point estimate. All the data, all the files I'm showing you now are available on a Dropbox, and I will email you the link to that Dropbox immediately after this session. Here is a Microsoft Excel spreadsheet with a large data set on it. Again, overlap with A-level. The new A-level, all the data handling is built around a large data set. We've invented our own for the purposes of this course. What you have on the screen here are 1,500 male heights. Trust me, it goes down to 1,500. And we are going to use this raw data as our population for demonstrating what we mean by the confidence interval on the mean you get from a sample. Now, the fact that was such a ridiculously long and convoluted sentence indicates half the problem with teaching this. It's all a bit meta. So here's how we did it with our students. In order to teach this part of the course, I am assuming that you have already taught your students, number one, what a standard deviation is and how to calculate it using either a calculator or a spreadsheet. And number two, and very importantly, they understand how to use the normal distribution. Now, would anyone like me to very quickly whiz through the normal distribution here? A couple of people have already said they're happy not to do that. You can see a guide to how to use this same data set to teach the normal distribution on an earlier video. So if you're happy, I will just go straight on to talking about confidence intervals rather than the normal distribution. Nobody's frantically texting me back. Oh, Kylane, I see you've got a microphone. Would you like to speak? Do you have any requests about what you'd like me to do here? Hi, Kylane, I can hear the background. Oh no, just pressed an error. Okay, right, what I'm going to do then is I'm simply going to wade straight on with confidence intervals. So, consider this set of 1,500 data points as a population. How do you take a sample of this population to get an estimate for the mean, and how confident can we be about this particular mean? Well, the first thing we do is come along, we number all our data points. So now I've just put the numbers 1 to 1,500 down the side of my 1,500 male heights. I've also used Excel to work out the mean and standard deviation of the entire population, and we'll come back to that later. But the important thing is, for taking a sample, that I've numbered all the data points. Now, what I'm going to do now is I'm going to tell the computer to generate some random numbers between 1 and 1,500 and use this to create some samples of different sizes. That sounds very messy. So let me just show you the next screen on this very nice spreadsheet that my colleague Lee did. Now let me talk you through what's on this. I presume, yeah, you can all see this now. Here is our data set, highlighted in column B. Here are the numbers, our identifiers on these data points. Here are a collection of random numbers. Now you'll see the first one says 1014. I have told Excel to generate a random number between 1 and 1,500. What Excel is doing is it's generating a random number, in this case 1014, going all the way down my table to row 1014 and picking out the number 169 and then popping it in there. It's then generating another random number and finding that data point, then generating another random number, and so on. You get the idea. Then what it very cleverly does is it does a running calculation of the mean of all these data points up to and including this one. So here, for instance, the first one that's highlighted in green is simply the mean of one data point. Well, that's a bit rubbish. That's just that one number there. Here, 179 is the mean of those first 4 data points. Here, the 180 is the mean of those first 16 data points. And maybe some of you have spotted, while I picked 1, 4, and 16 as my sample sizes. Now, I spent some time talking to my students about how the computer is doing this, because it's important that they understand this is a random sample of 1 or 4 or 16 members of the population, and I'm taking a mean based on that sample. Then what I do is I start pressing F9 on my computer, and every time I press F9 it finds new data points and calculates new means. And what I do is I simply say, right, I am now going to press my F9 button 10 times. And I want one of you to keep track of the highest and lowest values for one data point, one of you to keep track of the highest and lowest values for 4, and one of you to keep track of the highest and lowest values for 16, and see what goes on. Well, I'm going to do this 10 times, and I'm just going to look at the top one. So if you look at the top one, it goes 180, 169, 179, 179, 175, 158, 172. You see the one that's a sample size of 1 is bouncing all over the place. We've already gone all the way up to 188 and all the way down to, is it 15 something? Whereas if you look way down here at the bottom, it's not bouncing around that much at all. What I'm trying to convey at the moment is the larger the sample I take, the smaller the range of values I get for my mean. That is the first really, really important point I want them to get out of this point estimate. The larger the sample size, the smaller the range. So that's the next big idea. What happens to the spread of these means as the sample size increases? It gets smaller. Now, depending on how confident you are with your students, how long you want to spend on it, I actually spent a full double lesson, 2 55-minute lessons, simply fiddling around with this spreadsheet. What I then did is I actually got them to write down lists of 10 or 15 means, recorded them, and actually put them in a histogram. So let's take our sample size of 16. I get 180, 176.7, 179.1, 175.8, 179.8. They collected all those values and plotted them initially in a group frequency table and then on a histogram. That's really quite time-consuming. But the miraculous learning point we had at the end of that lesson was, because they'd already been taught about the normal distribution, when they plotted those means in a histogram, they found that the distribution of the means formed a kind of normal-looking distribution. This bell curve suddenly popped up out the data. If they get nothing else out of this whole exercise, they've got a far better chance of understanding confidence intervals once they realize that this mean number here has its own distribution. And that distribution is a sort of bell-like thing. Now, if you really want, what you can do is you can then show that, in fact, the relationship between the range for, say, 4, and let's do this for, I'm going to do this for a sample of 10. I'm just going to make a note of the highest and lowest values. So 180.5, 2, I've got 183, 3, 173, 4, no, that's not lower, 5, no, it's not higher, 6, no, it's not higher, 7, no, it's not higher, 8, oh, we're up to 184 there, 9, 10. I just took 10 data points there. My lowest value was 173 and my highest value was 184. There's a range of about 11 on those data points. If I now take 10 samples down here and look what happens to this mean, well, my first one looks like 176.9, 2, oh, also 176.9, 3, 176.3, 4, oh, 177.7, 5, 179.3, 6, 182.2, 7, oh, back to 1792, 8, 1788, 9, 1798, and 10, oh, 1773. So it looks like my sample now ranges from about 177 to about 182. Up here, for a sample of 4, I got a range of 11. Down here, for a sample of 16, I got a range of 5. In other words, I've kind of halved the spread by increasing by a multiple of 4. What I'm trying to get over is the big idea of a sampling of a standard error, which is related to 1 over the square of the sample size. Ultimately, what I want my students to learn is sigma, the standard deviation of the original population, in this case 7.1, divided by the square of the sample size, or the square root of the sample size, gives you the standard deviation of this mean here. I hope that made some sort of sense. What we then did when we taught standard errors and confidence intervals was every time I did an example, I showed two different graphs. And I can probably pull up the actual screen I used here, but I'm not going to because it's not prepared. I have prepared that in my slides. So I would have an imaginary normal distribution curve for my population where the mean we don't know, but the standard deviation we do know. And then in a different color, I plotted the normal distribution curve describing my means. I get a mean out of it and I get a standard deviation, an estimate for the standard deviation. That's what we call the standard error on this. So I get two different normal distribution curves, one of which relates to my sample and one which relates to my population. And we use this one here to draw inferences on what happens back there. I hope that made some sort of sense. That's how we did confidence intervals with both our Year 13 classes this year, and it worked extremely well. So, if I go back to my presentation here, that is what we did. Introduce the idea of a point estimate, an estimate based on one estimate for the mean, based on one sample of 5 or 10 or 15. Investigate what happens to the spread of the means, how the mean jumps about as the sample size increases. And then 3 and 4 are really optional. It depends on how far you want to go with your particular class. I didn't go into a huge amount of detail with this. I went through it. They smiled sweetly, but I'm not sure how much they really understood it. However, they did get the idea that the spread of the mean decreases as the sample gets bigger, so when I started writing sigma over n squared, it made some kind of sense. Right, that's confidence intervals. The next thing we talked about on Wednesday, and something which you might be interested in, is doing virtual lessons. We've come up with this strategy at Marylebone because we're really quite concerned about funding this course in the future. We've got about 12 students doing it in year 12 at the moment, 10 or 12 students, which is fine. That's just about viable. You can run an A-level class of 12. However, what we found last year was that we started off with 12, but quite a number of those 12 did not come back in year 13. And now we're in this ridiculous situation of having 2 classes of about 3 students. We simply cannot afford to continue to do this. So we're biting the bullet and seeing it through this year because we started it last year with funding, but that ain't going to happen again. And the only way I've been able to sell the course to senior management is to say, right, what we can do is we can schedule 1 lesson per week, an hour-long lesson per week, with a maths teacher, an experienced maths teacher in the room to teach this, and the rest of it they'll do as sort of flipped learning. That does not mean sending them off to do stuff at home. So here is the way we are conceiving of it, and then I will show you part of a video that we've actually created as an exemplar for how this might work. So here's the plan for how we will do this with video lessons. Students are timetabled to do this course for 2 or ideally 3 lessons per week. The official quota should be 5 lessons a fortnight, but that doesn't work for our timetable. It's either 2 or 3 a week. So here's our plan. Lesson 1, students watch the video, such as the one I'm about to show you, as a group in a classroom. They might need a support teacher. They might need whoever is in charge of the study room to duck in. But we try and get them in a room to actually watch this thing. They watch the video in the classroom, and then they work through some of the problems, and I'll show you the video comes with a set of problems. They work through some of the problems together in that room, rewinding, going back through the video for insight as necessary, but they try and struggle through the stuff together. So that's lesson 1. Lesson 2, individual study. They do a limited amount of individual work, probably at home, or it could be done in a room. The way our lessons work is it would probably be a double and a single, so the watching the video in a group is likely to be the double, and then the teacher will be budgeted for a single lesson where they will turn up and have kind of almost a university-style supervision, having worked on the stuff together in the lesson. And then number 4, they have a more conventional lesson, but it will be based on the assumption that they've already done the stuff. Now, there are clearly issues with this, but let me show you how the video works, how the questions work, and then if people do have questions or comments they'd like to make, do make them. If you can't get through to me, then I'll tell you what emerged from our discussions last week. So right now I'm going to show you this video. There is a problem with this GoToMeeting software. It doesn't actually pick up sound. So I'm going to have to revoice this video as we go through it. So let's hope this works. Here is my Fermi estimation video. And this is what the students would watch in their first lesson. And I'm going to have to mute my student. Hello, and welcome to this lesson on estimation with me, Mr. McIver. We're going to be working through some important issues to do with a particular type of estimation that you may not have encountered before. The sort of estimation that we're going to be looking at today is really rough estimation. And as ever, because it's maths, we've got a special name for this sort of mathematical estimation. It's called Fermi estimation, and the problems are called Fermi problems. Now, Fermi was a physicist, brilliant physicist, a bit of a mathematician too, in the mid-20th century, who was legendary for being able to make really, really good, clever estimates for problems, for the solutions to problems, with apparently completely inadequate information. Now, what he did was he did what were called order of magnitude estimations. So these figures here, 376, 292, are in the hundreds. He was only trying to estimate to an order of magnitude. Is it hundreds? Is it thousands? Is it tens? Is it millions? Just to give you a wee bit of background, Fermi was a physicist who worked on the Manhattan Project. They built the atomic bomb in World War II. Wherever you think about atomic bombs, I'm not a great enthusiast for them myself. Fermi was very clever at these sorts of problems, and what he did that was brilliantly clever when they carried out the first test is he tore up some bits of paper as the bomb went off, dropped them, and simply by measuring the distance they flew back, estimated the yield of the bomb as 10,000 tons of TNT. He did that by getting out his ruler and measuring the distance some bits of paper fell. In fact, as it turned out, the real figure was about 20,000. So Fermi's estimate of 10,000 was remarkable. The classic Fermi problem is how many piano tuners are there in Chicago? Now, on the face of it, this looks completely impossible. Here you are, a piano tuner in Chicago, and how many pianos are there in Chicago? How many people are there in Chicago? How many piano tuners does it take to tune a piano? How many times a year does a piano need? There are just far too many unknowns. Now, what Fermi did is he did everything by estimating in powers of 10. So the first thing he had to do is come up with an estimate for how many people live in Chicago. Well, it's a pretty big city, so it's probably in the millions. Is it 1 million, 2 million, 10 million? At this point, people's heads often start to, well, explode. But this is where Fermi estimation comes into its own. Chicago's a big city. It's probably got a population in the millions. So let's just estimate the population as 1 million. 1 followed by 6 zeros. Okay, 1 million people in Chicago. Oh, by the way, the actual population of Chicago is 3 million, but in terms of really rough estimations, 3 million, that's okay, because it's in the millions. Right, so there is our Fermi's estimate for the population of Chicago. Next thing, how many pianos in Chicago? Well, the smart way to do this is to say, how many people in Chicago have pianos? Is it 1 in 10, 1 in 100, 1 in 1,000? Well, given that this estimate includes babies and small children, let's guess 1 in 100 people in Chicago have pianos. So, 10 to the 6 people in Chicago, 1 million. 1 in every 100 has pianos. Multiply these two numbers together, and we've got a figure for the number of pianos in Chicago. Brilliant. 10,000 pianos in Chicago. So how many piano tuners do we need? Well, once again, we could go into all sorts of complicated ways of thinking about this, but the trick is to think of it in a simple way. Why don't we just ask, how many pianos can your average piano tuner tune in a day? In a year, I beg your pardon. Well, I suppose there are 365 days in a year, and a piano tuner can get to, well, you can't exactly bring the piano in, can you? He has to go to their houses. Piano tuner can go to 2, maybe 3 houses a day. Okay, so the number of pianos a tuner can tune in a year is probably in the hundreds. Okay, let's just call it 100. Right, so we've got 10,000 pianos. We've got, each piano tuner can tune 100 pianos in a year. So we simply do the sum, the number of pianos divided by the number of pianos one tuner can tune in a year, and we get 100. That's our estimate for the number of piano tuners in Chicago. Now, you'd be entitled to think, how on earth is this supposed to work? We've just made all these really, really wild estimates. The assumption with this kind of estimating is that some of our estimates will be too big and some will be too small. They'll balance each other out, and somehow the overestimates will balance the underestimates, and we'll end up with a sensible figure. Somebody looked up the Yellow Pages in Chicago and checked out the number of piano tuners in Chicago. According to the Yellow Pages, it's 81. So our estimate of 100 was really remarkably good. So thanks to TED Talks for that video. Now, I'm now going to show you how to do it with some problems of your own. How many pupils are there in our school system? We're going to do this whole thing with powers of 10. But the first key thing we need to do with this question is ask, how can we reframe this question? Now, in this country, school's pretty much compulsory from 5 to 16. Most people stay in it till 17 or 18 in full-time education. So we can actually turn this problem into how many 5 to 18-year-olds are there in the UK? Well, to come up with an answer to that, it's useful to some general knowledge. It would be useful to think, well, how many people are there in the UK? No idea? Okay, let's write down some really, really round figure estimates. 100,000, 1 million, 10 million, or 100 million. Now, you really do need to know a bit of general knowledge here. I'll show you at the end a screen showing you the information you need to know. It helps to know that London's got a population of just under 10 million, and there are quite a lot of cities in this country, so 100 million is probably the most sensible guess of those figures. 1 billion, you really ought to know that 1 billion is more people than there are in the UK. So 100 million people live in the UK, that's our estimate. Now we want to know about particular ages, so I suppose the next question is, how long do people in the UK live? Okay, let's come up with some possible numbers for the age that people live to in the UK. And here are some numbers. 1, 10, 100, or 1,000. All pretty stupid numbers, but the only one that's remotely reasonable is 100. So okay, we've got 100 million people living till they're 100. And those of you in the know will have realized that those are two overestimates which will cunningly kind of cancel each other out. So let's now go back to the problem of saying how many 5 to 18-year-olds are there? Okay, let's think of this visually. If we had a big line representing all the people in the UK, so there you are, that line represents 100 million people, and people live till they're 100, okay? Let's chop it up by years, 10, 20, 30, 40, 50, 70 years. What we have is 1 million people in every 1 year interval. Well, now we're getting somewhere, because now we just overlay this picture with our 5 to 18-year-olds. Where do the 5 to 18-year-olds go here? Well, I guess they go down at the bottom, somewhere around about here. Okay, there you are, 13 years. 13 years, roughly 1 million people in every 1 year interval. So I'm supposing that means about 13 million people. Now, we've done this really roughly, so I guess we ought to round that off to about 10 million to keep it a proper rough estimate. Remember, all we're looking for is an order of magnitude, the right number of zeros. Okay, let's see how good our estimate was. I actually went online and dug out the school census figures from the DFE for last year. And here they are. Here is a spreadsheet that shows us all the kids at school in the UK. Rather a lot of numbers there. We've got under 5s, we've got 5s to 10s, 5 to 16s, up to 19 pluses. It goes up to 19. Let's just look at 5s to 19s. That's the best figure I'm going to get off this data set. When I added up all those people from the official government figures, I got a grand total of, drumroll please, 13,881,000 blah, 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 as opposed to our estimate of 13 million, which is kind of impressive given the off the top of our head estimates. So that is the secret of Fermi estimation. What I'm going to do now is I'm going to leave you with some useful data that it is helpful to know. And keeping those useful bits of data in front of you, useful figures to remember, I'm now going to give you some problems to work on. And at this point, my students in their imaginary room will work through these questions together using the data I've left with them. Now, I don't know how many of you have seen that video before. I sent it round to a few people. Did you like it? If so, would you like to see some more? And if yes again, any particular topics that you'd like stuff on? Do answer. Because I'm going to post this up afterwards, I'm not going to leave the video with too many long silences, although I realize this has been an awful lot of me talking. For your information, oh, Colleen, do you want to speak? You've got a microphone. Hi, Colleen. Oh, I need to unmute my speakers. Hang on. I can't.
Can you hear me?
Oh, I can hear you. Great. Yeah. Hi, Colleen. Yeah.
Yeah, I had to unmute myself. Yeah, I did enjoy that video, and this is one thing that we were sort of struggling with. My colleague, but she doesn't actually teach on the course anymore. She was much better at this than I was. So thank you very much for that video. And I think that bit about, using powers of 10, it helps a lot. It helps a lot. Kind of makes it easier for our students. What was I going to ask?
what we're planning to do at Marylebone is make a set of these because we can't afford to run all these lessons next year. But we're going to start recording them next month. Do you have any requests for stuff you would like now? And other people do type in because we are getting some recording equipment here with Maths Hub money, so we'll build them.
Oh. Can we have something on student loans and the taxation?
Oh, easily done. We've got some extant stuff on that. I can certainly create some stuff on that. That would be very easy to do quite quickly. One of the topics that's come up a lot from everyone is this stuff on critical analysis. Number one, what is critical analysis? What does a good answer look like? The kids get torn between either writing and writing and writing reams and with no numbers in, and you just say, well, that's a lovely story, but it's no marks, I'm afraid. Or they do loads and loads of sums and then don't say what any of them mean. And it's a really hard skill to learn.
Yes, yes, it is.
So I will certainly be doing some on critical analysis. But yeah, student loans, taxes, very easily done. We can get those up very quickly, actually. Okay. In that case, I will move on if there are no more pressing questions on that one. By the way, this is a very inequitable. I could see you there, Carlene, and you couldn't see me. I don't have a webcam on this. If I go back to my PowerPoint, here you are, my virtual lessons. That's our cunning plan for how we're going to do it. What we're going to try and build up by September of next year is a library of between 20 and 40 of these things. We've worked out that about 10 minutes is a pretty good length because you can make them quite dense. People can rewind and look at them again, but they get more of the time to work together on the problems you've left. So we're looking at 10 to 15 minute videos. Oh, and in case you're interested, this type of course is called a SPOC. You may have heard of MOOCs. You may have heard of other things. Massive online courses. A SPOC is a small private online course. That's what we'll be setting up. But these videos are being made with Maths Hub money, so you're all entitled to them. Right. So we've looked at teaching confidence intervals. We've looked at the video approach to virtual lessons. Working with the IOE. When we met on Wednesday, we had someone from the IOE, so I'm simply going to show you a screen now with what she said. The Institute of Education actually runs free courses for recently qualified teachers. Little bit vague here. If someone's been qualified for 10 years, they probably can't really do it, but they don't necessarily have to be a beginning teacher or an NQT. But if they were a beginning teacher, they wouldn't have time there. They'll have other stuff on. And the courses that they run are fully funded for state institutions. They can take the form of either 10 online sessions or 3 days face-to-face. So if you need additional support, they're targeting more at A-level, but in fact, I'm working with this person here, Jenny Golding, on the core maths component. So if you've got teachers that you think would benefit from a sort of ongoing support package for developing their Key Stage 5 strategies, the IOE has this available. And that's the email to use. Jenny Golding, very appropriate. She'd love to hear from you. Finally, the new revision guide, which is coming out from Let's Study Guides in the spring. Not a great deal to say about that other than it is designed for the AQA specification. So if you're doing OCR, there's quite a big overlap. If you're doing Edexcel, I'm not sure if this book is going to be very helpful because here is the content. At the moment, it's 4 chapters, then 3 chapters. It's proving a bit knotty to write because normally it's a revise in a week. The guide is going to be called Revise Core Maths in a Week or Revise Math Studies in a Week because there is an established Let's brand of Revise in a Week. that would normally mean 7 chapters, but because of the optional bit of this course, it actually means 13 chapters, so it's taking slightly longer to write, because of course, depending on which of these strands your students are doing, they will only do one set of these 5, 6, 7s, but that's 9 chapters to write. Anyway, that's going to be the format of the book. That is due out early next year. Well, when I say early, I would be very surprised if it's out much before the end of March, because I know the people who are writing it. However, the Core Maths exam may, having a single volume slim revision guide for the beginning of April, for the start of the Easter holidays, could be a real godsend for your students. It's on its way, and I'll keep you posted. So that is what I said we go through today. The teaching bit was the bit on confidence intervals, virtual lessons on video. I just showed you one of our video lessons. You've heard about working with the IOE and the revision guide that's coming. Just to let you know, the next Core Maths session is on Wednesday the 1st of February, and there's another one on Wednesday the 22nd of March. As before, they will be followed up by sessions like this online, so if you can't make the meeting, don't worry. For those of you who are interested in the A-level changes, because those are going to be preoccupying us all, we've got one planned for Wednesday the 18th of January. The hope is that by that day, some of the A-level exam boards will actually have had their curricula signed off by Ofqual, so we will have the true specifications. However, those specifications have only just gone to Ofqual, having had the first lot bounce back for revisions. We may not have all the information we really need by the 18th of January, but we thought it was worth putting something in the book. So as you can see, we've got 4 sessions next year, 2 next term, 2 on Core Maths and 2 on A-level. And that is the end of this session. So does anybody have any questions that they'd like to type or ask if you have a microphone?